Welcome everyone. My name is Shelby Arendt, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards program and is co-organized by myself, Jen Perkins, and Jamie Kostelnik, with help from Stephen Slaughter. For those of you who are new to this meeting, you can submit questions via the chat window or use the raise your hand feature along with your microphone and video camera. We'll wait till the end of the presentation to take questions. In the meantime, please do your best to make sure your microphone is muted when you aren't intending to speak. It's my pleasure to introduce Carrie Ann Hancock, who is a senior geoscientist at BGC Engineering. Carrie Ann studies geohazards and how they affect communities and infrastructure in British Columbia, Canada. She's also passionate about how wildfires interact with unstable slopes north of the 49th parallel. Today, she's going to present some of her work on landsliding and river instability during the November 2021 atmospheric river event in British Columbia, which caused extreme flooding and landsliding. And this work has recently been picked up by the press. So if you want to read more, a quick Google search took me to 4 or 5 recently published articles as well. But with that, you can take it away, Carrie Ann.
Okay, thanks very much. Yeah, I'm back at the USGS Landslide Seminar. I had the pleasure of presenting with my colleague Matt Latto a couple of years ago on some sort of preliminary findings that we had after the event. And as mentioned, my colleague Kyle Valarchuk and I put together this paper that got published earlier this year and actually got picked up by the media a couple of weeks ago. So it's been a bit of a frenzy around here. The QR code will link you direct to the paper. If you don't have institutional access, I'm happy to provide a copy by email. Unfortunately, the open access fees were quite pricey, and so I wasn't able to make it open access, but I'm happy to provide the paper to anyone who's interested. I wanted to start today's presentation by acknowledging I'm coming to you from Vancouver, which is the traditional and unceded territory of the Squamish, Tsleil-Waututh, and Musqueam nations. And then the place names that I'm going to use today are in English, but the atmospheric river affected a large number of communities, First Nations, unceded territories of those nations. And in particular, I want to tell you a little bit of a story about 2 different individuals that I have had many discussions with. And the picture that you can see here is former Chief Arnold Lampreau of the Shakin Indian Band. And this is one of the pictures of near his house, where you can see the river was actually washed out during the flood in 2021. And it was actually the conversations that I had with Chief Lampreau and with David Lawrence of Nouriach Band, who were asking me these questions about, well, you know, what were the landslides like upslope of us? Why were these floods so bad? That really sparked the curiosity for this research and in doing this work, and actually kind of encouraged me to keep going on it because I did a lot of this kind of on my own time and off the side of my desk. So just really gratitude to these individuals for sparking this conversation. And ultimately, the results bore out kind of some of the questions that they had to me about what the different landslides were. So to understand the context of what we saw during the November 2021 atmospheric river, it doesn't just start in November. You have to know that in 2021, we had a historic heat dome occur in June, which then led to a very severe wildfire season. And then we had transitioned into a wetter than normal fall. And then on top of that, having these November and December atmospheric rivers. So we had a number of different climate change driven weather events in 2021 that sort of complete the picture of why we saw a number of damages that we did. It wasn't just because of one individual event, but the accumulation of all these different events occurring. If you're not from the Pacific Northwest, this may have landed in some cases around the world in terms of the news. But we saw this significant atmospheric river event from November 13 to 15, 2021. And this is a picture or a video here from NASA that just shows the atmospheric river water vapor that's coming through, as well as the total accumulated precipitation. And so you can see that band of that moisture extending, almost across all of Washington state and into a large chunk of southern BC, and almost all the way over into Alberta, so almost across the entire length of British Columbia itself. So quite a widespread event, and even down in Washington, some of the folks that I've talked to have mentioned kind of the number of landslides that they saw during that time as well. So for the purposes of this talk, what I really want to describe is kind of both this prolonged nature of rainfall, but also the intensity of the rainfall. And these are some of the totals that we put together for the paper in terms of the total accumulated precipitation. So the left panel is looking at the total rainfall that occurred in a 6 and 24-hour value during the peak of the storm, and then what the return periods of those were. So for context, 100 millimeters of rain in Vancouver, that's a pretty wet day, but it's not abnormal to get that around here. It's maybe kind of an annual event. But getting something like 100 millimeters of rain as you go further into the interior of BC is actually a very, very rare event. And in some cases, as we pushed over into the BC interior, that becomes something like 100 or 1,000-year event. So we saw this prolonged and intense rainfall push into areas of the BC interior that are not used to kind of seeing this. They kind of pushed up and over this drainage divide that separates the coastal mountains from the Cascade Mountains and into the BC interior. And when I describe later kind of some of the trends in some of the geohazards that you'll see that the core of the geohazards really were in those events. We did see some, kind of events further into Vancouver, but really the core of what I'm talking about today is going to focus in on this area in the BC interior. So during this event, as Shelby mentioned, we saw widespread flooding and landslides, almost $2 billion worth of damage across British Columbia. The image that you can see there on the right is the 4-lane Trans-Canada Highway that goes into Vancouver. So that was shut down entirely during this event. I managed to kind of sneak through here just about 24 hours beforehand, before the highway got overtopped. But at one point, Vancouver was effectively cut off from any of the large highway corridors that go in and out of British Columbia. And on the left, you can see one example of the widespread landslides that we saw. So we had both these kinds of events, widespread landsliding and widespread flooding. In addition to all of the property damage that occurred, we also had 6 fatalities during this event, 5 due to a debris flow near Pemberton, and 1 due to bank erosion along a river system in the interior. So I was working on responding to this event just shortly after it happened. The photo that I just showed there, that's actually me up in a helicopter doing infrastructure damage triage, beginning to kind of look at what might be necessary to get infrastructure back up and running. And we began kind of collecting all these events. So we at BGC, as well as a few other colleagues, the image there that you can see on the right is all of the different photo locations that we took over about a week time span during the response to the atmospheric river. So we were collecting these data points, thinking about where they all occurred, and we also at the same time began collecting lidar data across large swath of areas, mostly to assist in infrastructure reinstation. We put together a paper within about 6 months of the event, some really quick summaries of what we thought occurred. So having colleagues from BC Hydro, local consultants with Drew Brayshaw at Statlu, as well as Environment Canada and BC Ministry of Forests. So we put this quick inventory together, all the sites that we knew about, and presented it at a conference in Quebec City the following year. So we kind of thought we knew what we did. But my colleague Kyle and I, as we were working on infrastructure projects, trying to get communities back online, beginning to do risk assessments, we started comparing notes with each other. And he was seeing a pattern from my data set in the landslides to his data sets in the river systems. And so he began to notice kind of some of these trends where there were landslides happening. He was getting more lateral instability in the rivers. And so we kind of teamed up to say, okay, let's take this data and expand it, see what we can do to kind of figure out what's going on. So we collected even more event locations. So we took that original inventory that was done within 6 months of the event, and we developed a systematic inventory of all the different kinds of geohazards. So I'm referring to here all the different landslides, all the different debris flows, all of the channel instability. And we used a variety of different methods to come up with this inventory. So we had Google Earth imagery, post-event Google Earth imagery within about 2 years of the event that was starting to be collected. We used HazMapper, which is a normalized difference in vegetation indices method. And the example here that you can see, that very dark color, is an area of relative tree loss, indicating a large landslide. And then I did some field work to understand where these different debris flows and debris floods were. And then we also collected a large number of reports and social media events as well. So we collected all of these data points in order to inform our inventory. We also had access to pre-event lidar data for different infrastructure in the lower mainland and into the BC interior. So we were able to collect post-event lidar within about a week of the event occurring, and then turn that around for lidar change detection within about 4 weeks of the atmospheric river. So the images that you see here are from Cambio Earth, which is a software platform that we use to visualize the results of this change detection. And so we were able to start doing inventory and volume calculations of all those different sediment inputs to the channel. So this example here on the left is a large rock slide in the lower mainland along a major highway corridor. I think this is about 50,000 cubic meter rock slide that actually blocked the highway and pushed several vehicles into a wetland below it. The image on the right here, I'll talk about a little bit further. This is an area of the Coldwater River near Merritt, and looking at the different patterns of erosion and deposition that occurred along that river channel. So what we ended up with was this systematic inventory of geohazards that were triggered by the atmospheric river. And this is what we understand to be the first kind of widespread systematic inventory of geohazards. There's no published provincial or national database of these events. So I'm really proud of kind of what we put together to kind of show all these different kinds of events and where they occurred. And as I mentioned earlier, what you can really see is this core of different events that occurred in the most intense part of the rainfall area. We also saw widespread landsliding in the Fraser Valley and in other areas, and then up into the BC interior. And from what I can tell in conversations with Environment Canada, we're very grateful that the snow line stayed relatively low because we did not see widespread events occur further east into closer to the Alberta border. And then the other thing that we did as a kind of adjacent to this was beginning to see these patterns not only in the geohazards, but in the lateral instability of the river systems. And so the darker blue that you're seeing on the screen here is all of the laterally unstable channels that we saw. So places where, we didn't just see overland flooding, but we saw severe bank erosion, avulsions, and sediment accumulation. So again, you can kind of see that pattern that it's mostly focused in this area of high precipitation. So what did we learn out of all of this? As we're going through these different event inventories and trying to figure out what's the connection here, why landslides and floods, and what did they mean to each other? So as I began to do this systematic inventory, I began to notice these patterns. There was geohazards occurring more frequently in areas of forest disturbance. And what I mean by forest disturbance is places that have either been logged or burned or altered in some way, such that the natural vegetation cover no longer remains at that site. And so I examined these different contributing factors. So looking at provincially available catalogs of cut block extents, as well as resource road locations, extents of former wildfires, and then things like road networks in and out of areas. So the left two images are what I consider a forest disturbance scenario, so logging or wildfire. And on the right is what we began to kind of classify as this lateral instability. So in this image, what you can see here is a river that has shifted over quite considerably. I believe this one took out a bridge in this location. And as that's shifted over, it's undermined the toe of a large slope and unraveled and caused a very large debris slide. And you can see another example over here. So we began to also collect this information about some of the contributing factors that were associated with these kinds of landslides. In the end, what we found was, about 46% of the observed geohazards were linked by some way to these forest disturbances. So about 17% of the events followed or were sourced within a previously burned area. And then 15 and 14% were either in logged cut blocks or started at or below a resource road. We had another 14% of landslides that were triggered due to channel undermining within a river system. And then a couple of smaller events, what we kind of term large landslides, where maybe this is a very large deep-seated landslide that might have sent off a small debris flow. And then a few selected places where we had, the influence of a road in an urban area. So there was a large number of naturally occurring landslides, these ones that have these no mapped contributors, but we also saw a large percent of them had some sort of forest disturbance contributing towards them. And I know a number of folks are particularly interested in this from the wildfire space. So as I was kind of digging into the wildfires, I was also looking at, okay, what were the ages of those wildfire scars that triggered events? And so in BC, we've had increasing severity and size of wildfires. And particularly over about the last 20 years, we've seen events become much larger and much more widespread. And so you can kind of see, here's the number of different wildfire scars that we've had, as well as the years since the wildfire at the time of the atmospheric river. And so normally when we look at, events that occur due to post-wildfire scenarios, we might think, okay, maybe you've got an increased likelihood in that first 2 years after that fire occurs due to naturally repellent or hydrophobic soils. But what we saw in this data was there was a number of different events that were outside of that typical maybe 2 to 5 year range. And we actually had 23-year-old wildfire scars that had more geohazards out of them than the adjacent sort of unburned or undisturbed watershed next to them. So this is a really weird scenario where that hazard, that increased hazard likelihood, persisted for much longer than we would normally expect. And I'll show an example a little bit later on about this kind of 20-year-old wildfire scar where it actually destroyed a house at the outlet of it, and talk about some of the reasons why I think this is happening in this case. We also observed widespread resource road failures in some watersheds, and the example that you can see here on the screen is of the Scuzzy Creek watershed, which is in the Fraser Canyon area. And in this watershed, there was more than 50 different landslides in this watershed. And in the example here, you can see these older resource roads that are kind of sneaking up the slope, and then either starting at or below the resource road. So about 200 of these events that we've mapped, we were able to tie it back to a provincial database that showed the activity state of that site. So about 45% of these originated at currently active resource roads, 11% at retired roads that are within the provincial database, and more than 40% were unmapped or uncatalogued as resource roads in the provincial database. So in some cases, these older roads are actually classified in the BC Road Atlas as things like a gravel road or a gravel trail, but aren't actually recognized as a resource road. And this has important implications for managing these risks moving forward, because if they aren't recognized as this persistent feature on the landscape, they could be under recognized for their hazard contribution as well. So as we kind of move downslope, what did this all do to the river system? And again, we kind of began to notice this pattern where we saw sediment being introduced from hill slope processes, from landslides. We began to see the rivers move around more laterally downstream. And so this is an example here with a Kubi Creek watershed. The orange extent is about a 20-year-old wildfire scar in that watershed. And then the greens are places where there has been either salvage or post-fire logging, and in some cases pre-fire logging as well. And so we saw debris flows enter that mainstem channel. And as you kind of begin to follow from those debris flows, you begin to see the river system get wider and wider as a result, trigger a landslide, and then come down into the main stem of the Nahatlatch River, where the river moved around 2 to 3 times wider than it did prior to this event. And it was kind of visually compelling for me. This is a site that I visited after the flood, and I've since visited. But there are 2-meter sized boulders at the outlet of Kubi Creek at the Nahatlatch River. And I'm trying to stand there and physically think about, you know, a 100-meter wide stretch of channel that has 2-meter wide boulders coming through there, and imagining how much and how high of a flow would have had to been coming through there in order to make that, or transport those boulders all the way down. As I mentioned, we had access to some pre-event LiDAR data. So as we were kind of thinking through this lateral instability question, we wanted to quantify this a little bit more. So we conducted this LiDAR change detection analysis, which is shown on the screen here, and tied that to the event inventory, which is shown through these different locations. And for areas of lateral instability, what we've described as either severe lateral instability or moderate lateral instability, those are places where we thought all these different avulsions, or we observed those different avulsions, as well as bank erosion. Kyle estimated that in some of those locations, the Coldwater River was eroding 50,000 cubic meters per lineal kilometer of channel. And for context, that's something like more than 200 Olympic-sized swimming pools of sediment being eroded per kilometer of the Coldwater River. So all of this sediment is being mobilized, transported further downstream. And in some cases, we actually saw that sediment travel hundreds of kilometers downstream from BC interior and into the Lower Mainland and the Fraser River Delta. So all of this sediment that was mobilized during these events all ended up further and further downstream. So why is this happening? And I'll talk about this a little bit further, but I want to kind of describe to you the pattern that we noticed in the data. So we saw these widespread avulsions, bank erosion, deposition. They were typically noted downstream of sediment inputs into the mainstem river channel. So I'll bring you back to the image that I showed you before. So this is a debris flow that's deposited just within the Coldwater River system itself. So the red's indicating deposition. And then you can see just downstream of there, we see widespread sediment deposition. We see some bank erosion occurring at the outside bends. We then see lateral instability with the blues, the erosion undermining a slope. Same thing occurring here. And then again, seeing these patterns of sediment deposition and bank erosion. So we were noticing a pattern that at these locations where there was sediment input to the channel, we noticed this severe lateral instability downstream of it. So what does this mean? We thought about this pretty hard. We were trying to connect all these different things that we were looking at together. Why did we see these different events occurring? What's the linkages to forest disturbances? What does it all really mean? And one of the things from someone kind of working in the post-wildfire spaces is thinking about why are we having these older wildfire scars activate? And I have to do a shout out to Andrew Graber, and I have had some productive chats in the past little while trying to think through all the different explanations for them. So this is a Google Earth image of the 2009 Brook Creek fire that occurred in BC Interior. And you can actually see in the time since that fire, this is an image from 2003, there's been relatively little vegetation recovery after that event. There are some limited conifers that have come back to the landscape, but in the large part, this area hasn't recovered naturally within more than 20 years after that wildfire. And then the right image, what you can see here is a debris flow and debris flood that passed through the village of Brookmere and actually destroyed a house right at the outlet of the channel. So one of the questions that I pose, and this is definitely an area that needs lots more investigation about why these older wildfire scars were triggering hazards, is this because of vegetation recovery? Have we sort of changed the landscape and the hydrology of these watersheds so much after that wildfire that we really don't have the hydrologic sort of resilience built into it? So the trees aren't absorbing the water is running off faster, not because of a hydrophobicity any longer, but it's no longer allowing it to contain that water, and instead it's running off into the channel and then flushing that sediment out. I think that's the mechanism that's going on there, but this is definitely an area that we need more research and more investigation into. And then the second part about this, why are these disturbed landscapes, why are we seeing these, geohazards that are occurring in them? And then we're seeing all of this lateral instability occurring downstream of it. And this was the one that really puzzled me for quite a while until I had to think about why are these disturbed landscapes a little bit different. So you've got two images here. One is a resource road failure near Pemberton, and then one, an older post-wildfire scar, about 5 years old, in the Spies Creek watershed. So from literature, things with Joe Gartner's volume model, or also older literature talking about resource road failures, is that we generally know that these kinds of events are larger than what would be naturally occurring debris flows. The other thing that we know at these sites is that there isn't really a natural buffer that you would see on, say, a naturally occurring debris flow site. So if this was a naturally occurring site, we'd probably have some sort of alluvial fan right at the base of the slope, and that debris flow would run out onto the alluvial fan, deposit the sediment before it translates into the main stem channel. But in the case of these resource road failures or post-wildfire events, they're either much larger than a natural one would be, resulting in a much longer transport distance, or in some cases, they have no natural buffer system between the bottom of the slope and the main stem channel. So that's our working hypotheses as to why we saw the sediment introduced into these main stem channels, which then went downstream into these larger river systems and became laterally unstable. And what you can really see in the imagery and many of these locations is this input caused this drastic lateral migration. So this is an example. This is again, kind of 4 lanes of a highway, sediment being deposited across of it, crosses down onto another road, and then ultimately into a river here. So in this kind of schematic that I've put together, you can see that the river kind of gets or meets this deposit of sediment and then gets pushed laterally downstream due to the deflection from the sediment. So that then increases the bank erosion on the side channel, which then introduces sediment and then deposits that further down here. And so we think this is what the mechanism is, and I kind of describe it kind of like a conveyor belt, that you start with a sediment pulse that comes in from these hill slope processes, and if they are much larger due to forest disturbances, then it begins to move the channel around quite considerably, and you can sort of watch it like a bobsled go down the hill from there. The other thing to note is the 2021 atmospheric air, at least for places in the BC interior, was unique for a couple of different reasons. So it was both intense. In some places, we were seeing rainfall rates of 10, 15 millimeters per hour persist for 6 to 12 hours. So for our climate, that's actually quite a long, intense duration. And so when you get these intense rainfall rates, particularly when we're in sort of this pre-saturated situation with a wetter than normal fall, we get more landslides occurring up in the headwater systems. And then because it's a sustained rainfall, we have more water moving through the system, resulting in more flooding and bank erosion. So you're getting all of these kind of complex feedback systems where you're getting sediment being introduced. That sediment has to be accommodated in the channel, and in order to accommodate it, it has to move around laterally. And then the thing that for me as a practitioner, what I really want people to understand is this isn't going to be the first major event. It was for me a really big wake-up call in terms of the kind of different compounding natural disasters that we're going to see. And so we're going to see an increased likelihood and intensity of heat waves, wildfires, and atmospheric rivers. And for context here, you can see an image of what BC looked like just before that June heat dome. So this is looking at the severity of the fire weather index severity. So just before the heat dome in sort of late June through early July, and seeing the dramatic shift in just a couple weeks of really warm weather. So with climate change, what we're going to see is these more widespread drought, wildfire starts potentially moving forward. On the opposite side, having too much water is also going to happen. So we're going to see more of these climatic swings and shifts. So Sharma and Derry put together a historic database of these different atmospheric rivers coming through. And the blue line is kind of analogous to Washington and parts of southern BC, and actually showing an increasing rate of large atmospheric rivers landfalling in this area. And those are also expected to increase with climate change. But it's not only the increased likelihood that we're looking at, we're also looking at the intensity of those different events. So an event like the November 2021 atmospheric river is going to become more likely with climate change, but we're also expected to see larger events than the 2021 atmospheric river occur in through 2050 and 2100. So our key takeaways for managing risk after this event. And you know, Shelby and I were kind of joking about this at the beginning of or just before the call was, it seems really intuitive that we should consider landslides and floods together. But in many of our governmental systems, those are actually separated, in some cases entirely different departments, different people studying them. But we advocate for considering these two different processes together. So if you're doing a risk assessment for a community, you want to be thinking about what is that landslide doing upstream that might be affecting the flood, which is going to come through my community. So not thinking about them separately, not treating them separately, but doing a holistic assessment of these different processes. What I kind of just described here, climate change is expected to impact the intensity of these different wildfire seasons and precipitation. We're very likely to see an increase in these kinds of geohazards moving forward, and also thinking about the knock-on effects of them. So, 3 or 4 years out from this atmospheric river, I personally am still dealing with all of the bank erosion that has occurred at these sites, and looking at these third, fourth, fifth order effects, like increasing stream temperatures due to bank erosion. So can we actually examine this in some other locations where we might, hypothesize that a watershed burns, be doing these kind of pre-fire, post-wildfire assessments and thinking about what would it look like if we had a fire, then an atmospheric river come through. For those folks that are dealing with wildfire landscapes, this kind of observation of seeing this persistence of flooding and sediment delivery on older wildfire scars, for me really speaks to the idea that we have to perhaps promote vegetation recovery and slope stabilization, particularly where these watersheds may have transitioned into different ecological zones. So there is some emerging evidence within the literature that some of these places with intense wildfires may not be naturally regrowing the same tree species any longer due to climatic effects, but also due to the intensity of the burn. And so thinking about, do we need to actually go in and manually or begin to promote recovery in some of these places in order to influence future potential flood hazards further on. Acknowledging that we definitely need more field work to understand how these different resource roads and logged areas contributed towards these hazards. Were they blocked culverts? Were they drainage redirections? What's actually going on at these locations? And kind of tied to the last point there, like understanding the locations of where those are is really integral to doing all of this. If we have an older resource road that's cataloged as a gravel road, we're unlikely to be managing it or managing the risks from it in a proper way. So having a systematic inventory of these different areas in order to manage those risks. And then the last point I want to make there is that, understanding, and particularly in the Pacific Northwest and BC, Washington, and Oregon, is really understanding what are the processes that are going on these older wildfire scars, and how long is this hazard persistent on the landscape for. So with that, I'll finish off just with some gratitude for a lot of different folks. As I mentioned, Chief Lampro with Shack and Band, as well as David Lawrence with the lands manager with New Edge, who really sparked the interest in this paper. I had a number of different collaborators who worked on either the previous iteration of this inventory or did some further work to help us do the catalog of these different events. And then Celeste Mellowship helped draft all the figures that you saw in the paper. All of the organizations shown there on the right are organizations that permitted us to use the lidar or the ortho imagery for our assessment. And so just kind of acknowledging that the amount of data that was collected during this event really helped inform all of these different hazards and some of the understandings out of it. So with that, I'll end and happy to take any questions.